So here is our solution to example 1. We're hopping in a little bit. All right, anything else we need on this one, or can we move on? Anybody move on? Thank you. All right. So let's go here. All right, so as I said before, when you're solving a differential equation, you're finding a general solution, unless they give you an initial condition that allows you to solve for C. And we call that type of problem an initial value problem. So that's what we have this time. Very similar problem. Again, we're going to separate our variables. So dy equals, parentheses, e to the x minus 6x squared dx. What do I do next? Integrate both sides. So I'm going to combine them into the same step. Okay? All right. On the left, we get y. We'll manage our constants on the right. On the right, we get our favorite integral. The integral e to the x is e to the x minus 2x cubed. And we need a plus b. So there's our general solution. They tell us now that it passes through the point 1, 0. So how do I get my particular solution? So I give 1 is 0. So my y value is 0. E to the first minus 2 times 1 cubed plus c. So solving for c, we get 2 minus e. So our particular solution, which I'll write yes, is y equals e to the x minus 2x cubed plus 1. The c, which is 2 minus, there we go. There is our solution. In here. Oh, there it is. Okay? So, when you are given an initial condition, there is no plus b. You're going to solve for the particular solution. Here and particular. Okay, questions on that one too? All right, let's move on. All right, so this one is a very similar example, but it brings in something that we need to consider. And in calculus, we love when it's just algorithms and we can just quickly go through problems, but there's a lot of thinking that has to go on based on the information we know about the function. So in this one, we are finding a particular solution again. So there will be no plus c. The function is dy dx equals 2x minus secant squared x. And it says whose graph passes through the point 0, 3. So let's go ahead and do that, and then we'll show what we need to consider in the end. So we separate our variables. Dy equals 2x minus secant squared x times dx. Again, we will integrate both sides. Y equals, what do we get? X squared minus tan x plus c. That's our general solution. So we have a point 0, 3. Let's plug that in. We get 3 equals 0 squared minus, what's the tangent of 0? It is 0. Plus c. So we get c equal to 3. So our general solution. Yeah. All right, so our particular solution is y equals x squared minus tan x plus 3. All right, so you notice where it says example 3, handling discontinuity in an initial value problem. So part of our solution here has places where it is not defined, right? Tangent has places where it is not defined. Where is tangent undefined? okay, or negative, generally for the first one, we see it negative pi hat and pi hat. This, this, and right? That's what our tangent looks like? Okay, so that means our particular solution, we say that it's pinned in at the point 0, 3, and it's pinned down for all of its continuous parts. Well, it is not going to be continuous jumping over pi hat or negative pi hat. So we need a domain restriction. I should write that out. Domain restriction. Does the point 0, 3 fall between negative pi hat and pi hat? Yeah. So our domain restriction then would be between negative pi hat and pi hat. Okay. So it's just something to keep in mind. When you find a solution to a problem, don't just move on immediately. You need to think about it a little bit. Are there any funny things going on with this function? Are there any restrictions? Okay? Yes?
Why is it?
Because when we find that particular solution, it only will work, it will only be a solution where the function is defined, where it is continuous. And this thing will be discontinuous at pi hat, so it can't jump over that. So we need to say it's between those two. Okay. All right, let's go on. All right, this is a problem in this book. I don't think I've run into it in my other book, but it was kind of an interesting problem. It kind of forces you to do a problem a certain way. So I just want, there are 1 or 2 like this in the homework, so I wanted to make sure you had seen them before. It says using the fundamental theorem to solve an initial value problem. What is the fundamental theorem of calculus? It is the integral from a to b, lowercase f of x dx equals capital F. What does that mean? What just happened? How do I get capital F? You take the hyperunit, yeah. C minus capital F. Okay. That is the fundamental theorem of calculus. Okay? In this case, it says find a solution to the differential equation f prime of x equals e to the negative x squared. So we're being asked to solve a differential equation that's in the form of f prime. So what am I looking for as my solution? When it was dy dx, we were looking for y. When it's f prime of x, we're looking for what? Not just x, but f of x. Lowercase f of x is what we're trying to solve for. Okay? We're trying to undo f prime. Well, if that's the case, that means they want me to use this fundamental theorem, and I want to have an f of x in it. And I'm starting with an f prime. So I'm going to rewrite my fundamental theorem from a to b. I'm not starting with f of x, I'm starting with f prime. So I'm going to write it that way. F prime of x dx. And what is the antiderivative of f prime? Lowercase f prime. Okay, just f. And then it's a lowercase f. I'll do my best to make a distinction here. Minus lowercase f of a. All right, we're trying to find lowercase f of x. So I'm going to use this, and I'm going to make one of my limits, not d, but x. So that way I would get an f of x here, so I can solve for that. Okay, so that means that my upper limit is going to be x. What do you think I will use for my lower limit, given this problem? for which f of 7 equals 3. Yeah. Since I know f of 7, I'm going to make my lower limit 7. And that means over here I'll have f of x minus f of 7. And we still have f prime of x dx is here. Okay. I'm trying to solve for that. Now, our answer, we do not know how to take the antiderivative of this yet. So our answer will have an integral statement in it. Okay? So how do I get f of x by itself? I add what? Add f of 7. So my solution is going to be, and I'll plug in what we know, integral from 7 to x. What is f prime of x? E to the negative x squared dx plus f of 7 equals f of 7. And then finally, what is f of 7? 7 to x e to the negative x squared dx plus 3. And there is the solution. My clouds are so much nicer on this board. There. Okay? So, one or two problems like that in the homework. Remember that you're going to have an integral in your solution that we're not solving. Questions? Okay. All right. Now, all right, so when we solve, here's example 5, graph the family of functions that solve the differential equation dy dx equals cosine x. Well, the solution is graphed right here. Right? It can be any of these, can it? Because if I take the derivative of sine x plus 1, don't I get cosine x? If I take the derivative of sine x plus 2, my answer is cosine x. So this is a representation of the idea of sine x plus c. Okay? So the solution to this differential equation, when we separate the variables and so on, we write it out. dy equals cosine x dx, and we integrate both sides, and we get y equals sine x plus. Okay, but it's a nice visual that leads us into our next topic, which is cosine. All of those are possible solutions to that one differential equation. And as I said, since we have some functions we cannot integrate, we need to have ways to come up with a graphical representation of our solution. So a slope field, which we'll see next, is a graphical representation of the solution to a differential equation. Okay. And we'll come back to this problem in a minute, but you have a sheet on your desk that we're going to do together. Yeah. Right. Slope field. Oh, let's jump off. Pass this down to and you guys gotta get class on time. And this is the last due Monday. That is what we're doing in class.
It's a lab, I don't think.
What's that?
It's going to be my toughest job. Okay, so let's look at our next example. And this type of problem comes up on the AP test quite often, and they're a little tricky because you don't know exactly what the range is on the windows. say. No, we don't. And what we have to do is match the proper slope field to its differential equation. Okay? So you could think, okay, well, let me just plug in some points and see if the slope comes out right, which is basically what we'll do, but we're going to be a little bit more methodical in it. And we are going to be a little more interested. Let's think about where dy dx equals 0, so where it'll have horizontal tick mark, and where dy dx will be undefined, where it would have vertical. So you want to look for where the derivative is 0 or undefined. So if we look in number 1, well, there's no fraction, there's no root, so it's not going to be undefined anywhere. So let's think about where this is equal to 0. And our derivative will be 0, where, if I move the y over, where y equals x. Well, that is the line, the diagonal coming up like this, correct? So what you want to do is look at the line y equals x and say, are the slopes 0 on that line for A? Are they? No, they're not A. How about B? Let's look at y equals x. So here's 0, 0. Here, right between those two tick marks, between those two, those two, those two, does it look like it could have flattened out? This one's a little hard. This is probably the trickiest one. It does. It looks like this graph would have to take a turn, right? If I draw one in, like this, I'm going to follow this, I'm going to go like that, and then up, without the hump. But right in here, we're going to have a slope of 0. That was hard to see. But I think that is the solution to number 1. I would say that it happens to be. We can check the others. Are the slopes 0 through here? Nope, they're not. And how about on the last one, if I can pull it over? You can see it. Are the slopes 0 up through here? Nope. So it looks like our solution is B. All right. The next one. When will this be 0? When x equals what? 0, or when y equals 0. So you want to look for a graph that has horizontal tick marks on the vertical line, the vertical axis, and the horizontal axis. So this one has horizontal tick marks on the vertical. Does it on the horizontal? No. How about this one? Do I have horizontal tick marks here? No. Let's hope it's C. Horizontal tick marks? Yes. And how about here? Does it look like the slopes would have to be 0 here? Yes. Answer is C. All right, how about this one? When will it equal 0? When what equals 0? Y. When will it be undefined? When x equals 0. So I can see vertical tick marks at x equals 0, and horizontal tick marks at y equals 0. Is that A or C? It is, careful, vertical tick marks at x equals 0. That's the vertical axis. There you go. All right, and finally number 4. It's 0 when y equals 0, and undefined when x equals 0. Does that make sense over here? So if x equals 0... Oh, Mike, did I look the wrong one? Oh, I skipped 3. That's not coming out right. Okay, hold on. So, this one is number 4 that I did, right? I'll put 3 over here. How about 3? So 3 is 0 when x equals 0, and it is undefined when y equals 0. That's better. So I have horizontal tick marks where x equals 0, and does it look like I have vertical tick marks where y equals 0? Yeah. The answer is? All right. All right, are we okay? And those are tricky. There's just no real way to make those a lot easier. You kind of have to work your way through. All right, so finally, let's find a little bit more accurate method for getting a graphical representation of the solution to a differential equation. All right, your book has a similar picture to this one, but there's a slight difference that I've seen in most of the calc books that I've taught, and I'd rather you think about it this way. It makes things easier later on. So, we have a picture of a function, which I'll call f of x. We'll call this f of x, if I get on the pen. Okay? And I have a point on f of x here. And then I have the tangent line at that point. Okay? And what I want to show is moving the distance to the right and finding the y value that's on the tangent line and the y value that's on the function. Do I need to wait a minute while you sketch? Okay. So again, my picture differs a little from your book. That's what it is. What Euler's method is a procedure to allow us to use tiny little tangent lines and moving along the tiny little tangent lines to the curve to model the curve itself. Okay? So we start at xy, and what I want to do is get another point so I can move along the function. So I'm going to move to the right, let's say, and some notation you need to be familiar with. Generally speaking, when you see a delta x or delta y, we're talking about the function. When you see dx or dy, we're talking about the tangent line. Okay? So if I move to the right a certain amount, well then I move to the right for the function, and I move the same amount right for the tangent line. So dx and delta x are always the same. But dy and delta y are not always. So if I move just a tiny little bit, we're going to say this is some tiny number like 0.1. Okay? If I move 0.1 to the right, well, delta y is going to be changed from xy up to that point on the function. dy is going to be the change on the tangent line. And if we're dealing with really, really little tiny movements away from the point of tangency, shouldn't my dy be relatively similar to my delta y? As long as I'm really close to the point of tangency, then we guys have done tangent line approximations, right? When we stay close to the point of tangency, we stay close to the function value. All right, so I need to find a way to figure out how much it's going to move on the tangent line. So I go back to the equation of the tangent line. So here is my point slope equation, right? Y minus y1 equals m times x minus x1. Yes? Okay. Well,
what are the coordinates of this point? It's on the tangent line. So, this point, come on. No. I did. Yep. All right. There we go. What are the coordinates of this point? X plus what? Dx or delta x. You can call it either one. I'm going to call it dx. X plus dx. That's a d. And, I need to go back there and do that. How about the y? X plus, or sorry, not x, but y plus dy? All right, so I use this point in my point slope calculation down here. So I do y minus, my y1 is y plus dy, equals, what did I do here? Why don't I have numbers? What is m on the tangent line? It's the derivative, yeah. The slope of the tangent line. So I replace m with dy dx times x minus the x coordinate, which is x plus dx. So simplifying, I end up with negative dy equals dy dx times negative dx. The negatives cancel, and to find dy, all I ever have to do is take my dy dx times dx. Now that doesn't mean much until we look at the problem, but that's very helpful. So start at, this is the important part for Euler's method. Find a way to find how much it's going to move on the tangent line. All right, I'm moving a little quickly here at the end. I apologize, but I want to make sure I get my example in for Euler. All right, so our final example is here. Lovely table. All right, so when I do Euler's method, I will always have a table. And just for a visual as to what we are doing. So we found our dy here, and we added it to our y value, and that black dot is our new point. Then we use the tangent line again. We use the slope of the function to help us find out dy again, and I move up that much. Okay? So I'm using the tangent line to create what the function actually looks like. Okay? And it's an iterative process. We go little bits at a time. Okay? So our table, which you need to make on your sheet, my table is a little different than the one in the book. If you like the one in the book better, you can use that, but this is the way I do it. So it says, let f be the function that satisfies the initial value problem, where dy dx equals x plus y, and f of 2 equals 0. Use Euler's method and increments of delta x equals 0.2. They're always going to give you your delta x or dx. Okay? To approximate f of 3. So that's why in my x table, I start at 2, and I go up by 0.2, because they told me that was my delta x. And I stop at 3, because that's the one I'm interested in. That's why it has the stars next to it. My y coordinate at 2 was what? 0. Okay? And then to find dy, so to find out how much to move up, we know to move over 0.2, how much do I move up on the tangent line? I take dy dx, which is x plus y, times dx. So what is dx? 0.2. So on each row, you're going to do x plus y, which is 2 plus 0 in this case, times the dx, which is 0.2, and we're going to get 0.4. So what do I do with that 0.4 to get my new y? Very nice. Add it to the y. 0 plus 0.4 equals 0.4. That new y comes down over here. That is the y, so 2.2. And then what? We do it again. We
do it again until we get down to the one we're interested in. So here we'll have 2.2 plus 0.4 times 0.2 0.52. And we add that to the previous slide, which is 0.4. And we get 0.9. That comes down a little slow. I think 0.92. Okay, and we continue to work this process. Let me just, so you have correct answers to go by. Fill in what I have on mine. You can. All right. Here we will have 2.4 plus 0.92 times 0.2, and we get 0.664. And we do 0.92 plus 0.664, giving us 1.584. And I'll just keep going. Seven. One. And I'll get this up online also, so if you don't get it all down, it'll be online. .465. Oh, hello. Let's see. 1.3. And finally, that is the one that we needed. So f of 3 is approximately 3.465. That's 5, sorry. What's that? Did you go ahead of me? Maybe it's different numbers. That's the 2.421 plus the 1.014. All right. You don't need to go any further because f of 3 was the one we were trying to approximate. So let me know what you can't see or what is unclear. Isn't it what? Louder.
3.4.
Here? Oh, maybe I just wrote the numbers down wrong. Hold on. I'm just copying them down. 3.4. Oh, it was 1.044.
Oh.
Yep, my mistake. So let's fix that. And
So, what's really the point?
One second, let me write this down. That's better. Thank you. All right. Homework is on the assignment sheet.